Hello, folks. How you all doing? Now, I normally do this thing. I teach speaker workshops, and I say to people, get there like 20 minutes early, get everything plugged in and everything. And of course, we just decided we were going to drop the sessions that got canceled yesterday, got slotted into lunch. So we've just done like a 90-second turnaround. It's like changing the tires on a Formula One car, only with more laptops and stuff. So yeah, but the good thing is, this is a talk about failure. So if anything goes wrong, I'm just going to pretend that it was part of the script. So, and yes, this is a failure is always an option. So those of you who don't know me, this is me, Dylan Beattie. I run a company called Versatile that I started in January 2020, so I could do lots of traveling and go around the world and talk to people, and worst business plan ever. But it's all right, it's slowly kind of kicking into gear. I'm a Microsoft MVP. I occasionally still organize a meeting of the London.NET user group. We're trying to get that back up and running after a hiatus of a couple of years. And I once invented a programming language in a bar as a joke that has become a programming language with 3 different implementations, and now I have to project manage the joke, because that's what open source does. But if any of you ever wanted to be a rockstar developer so you can go and apply for all those jobs on LinkedIn, go to codewithrockstar.com, type in a program. The more it looks like an 80s heavy metal song, the better. That's the whole idea. And if it compiles, then you are a rockstar programmer, and you can go and get all those sweet jobs on LinkedIn. Now, the title for this talk is sort of loosely paraphrased from a line in this movie, Apollo 13. There's a point about an hour into that film where this guy, so this is the actor Ed Harris playing Gene Kranz, who was the mission director on the real Apollo 13. And he comes out with this great line, failure is not an option. Now, Gene Kranz didn't say that. Well, actually, he did say it, but he didn't say it in 1972 when Apollo 13 was happening. This is Gene Kranz, and he said that in an interview with the people who wrote the screenplay for the movie. They were talking to, all of the people who'd been involved in the real-life mission, Apollo 13. And at one point, apparently, they're saying, what were you thinking when you started getting all this telemetry data? And Kranz says in this interview, we realized that, we had to bring the people home, that failure was not an option. And apparently they looked at each other and went, that's it, that's the tagline for the movie. And then he borrowed his own line back from them, and that became the title of his autobiography, which has a lot of really cool information about, working on Apollo and Apollo 13 particularly. But by this point, by the point in the movie and the story that it's based on, when he says failure is not an option, they have already had one crew member have to be pulled out and replaced because he was suspected of having measles. They've had a main engine shutdown. The Apollo launched on a vehicle called the Saturn V. It's called the Saturn V because it's got 5 engines. A couple of seconds after launch, one of them just stops working. And we're talking a big rocket engine, but they're like, it's fine, just switch over, we'll burn the other 4 a little bit longer. And by this point in the Apollo program, Apollo 13 was the 13th mission to carry that designation. They had had all sorts of failures, from trivial mechanical component failures to fire on the launch pad, which actually killed the 3 astronauts on Apollo 1. So to understand what he means by failure is not an option, you have to understand the context. You have to understand, what is the definition of success that is relevant at this point in that narrative. Now, the Saturn launch vehicle, it had 99.9% reliability. That's what they were shooting for. It had 6 million components and moving parts. So a successful mission was one where only 6,000 things went wrong. That was their definition of a successful launch for that. And one of the engineers who worked on the Apollo system was this lady, Margaret Hamilton. She was the first person to use the phrase software engineering. And she was a huge advocate. She led the team that built the guidance software that took Apollo to the moon. And she has this quote. She says, you begin to think in terms of modeling all of these things as one system. Part of it is realized as software. Part is realized as peopleware. Part of it is realized as hardware. And that was the principle behind systems thinking. You know, we need to look at not a question of did this component succeed or fail. You need to keep stepping back and you're like, well, what does success look like? And what does that component mean in terms of the assembly that it's part of? What does that assembly mean in terms of the machine? What does the machine mean in terms of the mission? What does the mission mean in terms of the goal? You know, probably the best user story of all time, land a man on the moon and return him safely to the Earth. You know, that's a hell of a definition of done, and it doesn't say anything about how they are going to accomplish it. And by Apollo 13, they'd kind of done that. You know, John F. Kennedy stood up in 1962, Rice University, and he laid out, this is what we are doing. This is what success looks like. People on the moon, bring them safely back to Earth. When was that marked as done? When was the mission accomplished? Well, maybe it was July the 20th. When they set foot on the moon. Or maybe it was July the 24th when they got back to Earth. But then they were in quarantine for a month in case they'd brought back any moon bugs. So maybe it was August the 18th when it's like, okay, we are now satisfied. We sent them there, we got them back, and we're pretty sure that they're safe. You know, these are the definitions of success that you need to kind of dig into a little bit. And, you know, this was the headline. This is the point when the world says, yes, we did that, July 20th, 1969. Incidentally, there's a game where how much can you change history using the smallest amendment to a newspaper headline, which has always made me wonder if they'd accidentally put an extra comma in that, and they'd be like, wow, there are plants on the moon, and they brought some back. But now, the mission after Apollo 11, Apollo 12, it became the second successful mission to land on the moon, but it very nearly didn't. Apollo 12 was struck by lightning twice during takeoff. Now, I want you to just imagine that. You're kind of strapped into this capsule, you and the other two crew members, in a thing smaller than a compact car. You know, you're kind of strapped in, you've got your space helmets on and everything. You are on 6 million liters of highly explosive rocket fuel, and suddenly there is a catastrophic bang, sound like an explosion, and all the lights go out. And you're thinking, what do we do now? And you know what they did? This guy. This was John Aaron. And John Aaron's looking at all these things on his dashboard. He's one of the people who's working mission control out there, and he's like, everything has failed, but the spacecraft still appears to be going up. Maybe the thing that has blown is the thing that tells us whether it's working or not. A thing called the signal conditioning equipment, one of the circuits on there. And they had a procedure. You know, you've got a rocket, 6 million liters of fuel on board, taking off into space. It gets struck by lightning twice. And NASA are like, all right, well, we didn't simulate exactly this, but we've simulated power failures before. We've simulated system failures before. And if you go back to this famous photograph of Margaret Hamilton, the console that is above her head there is the main instrument console on the Apollo capsule. And it includes this little thing down in the corner. This is the signal conditioning equipment, and it has two power supplies. It has normal and it has auxiliary. Failure was clearly an option because they put a switch on the dashboard that you could flick if you realized that there was no power going to the signal conditioning equipment. And if that hadn't worked, they had a whole bunch of other options, up to and including a thing called the Apollo Launch Escape System, which was basically an ejector seat. It could fire the astronaut capsule off the top of the rocket, ideally just before it exploded, and that would then parachute back to Earth. Now, this thing was never used. You know, the Saturn V and Apollo, it has the remarkable pedigree. It's one of the few rockets in history that never blew up. And the full quote that Gene Kranz is referencing at that point in the movie was this: "We've never lost an American in space. We are sure as hell not going to lose one on my watch. Failure is not an option." So at this point, this context, failure means losing an astronaut in space. That is the definition of success that they have reframed and decided this is what we are optimizing for now. This is what we are going to try and accomplish. Now, Apollo 12 went to the moon. Apollo 13 got headlines because a lot of stuff went wrong, but they did, not to spoil the end of the movie or anything, but they get them back to Earth safely at the end of it. And they flew a bunch more Apollo missions, but everyone was kind of getting a bit bored. Because Apollo 12, 13, Apollo 14, the most interesting thing that happened was Pete Conrad took up a golf club and he hit a golf ball on the moon. Apollo 15, they sent up the little moon buggy so they could drive around. Apollo 17 was the last one, the only one that ever carried an actual scientist as opposed to just astronauts and pilots. And then that was it. They're like, yeah, we're not going to do any more of these. But they had something else in the works. They had the Space Transportation System, thing that everyone knows as the Space Shuttle. Now, the Space Shuttle was never actually a thing. It was a nickname. The Space Transportation System, consisted of the orbiter, the external fuel tank, massive orange thing underneath with all the fuel on board, and these two solid rocket boosters, one on either side of it. And the Space Transportation System, the Space Shuttle, the first shuttle flight was in 1981, and it incorporated an awful lot of ideas from Apollo. Lots of technology got reused, lots of systems, lots of components, but it also incorporated loads of new stuff that NASA had never flown before, including something called a fly-by-wire system. Now, fly-by-wire is historically aircraft, spacecraft, there would be mechanical connections between the things that the pilot moved and the control surfaces and valves that made the aircraft or the spacecraft maneuver. Fly-by-wire, you push a button or move a lever, it tells the computer what you did, and the computer works out what to do with the aircraft or spacecraft to make it reflect that input. And the shuttle had a fly-by-wire system on board, and the guidance computer system that it used, basically once it's in space, it can kind of stay there while you figure stuff out. But during launch and during landing, those are the critical times when they couldn't afford anything to go wrong. Now, to understand how they approach this, we got to think a little bit about how software fails, how systems fail. There are three different failure modes that we kind of get. You imagine you open up your laptop, you go to a website, and you get this. You just get straight away, error message, that didn't work. Something is wrong, here is the error, it's your problem now. Or you get this, and you wait, and eventually something is going to give up. You are going to lose patience. Your network connection is going to say time out. The infrastructure is going to go, there is nothing on the other end of this. Or eventually you give up. But the third failure mode is you get something that looks right, but it's not right. You get results which are plausible, but are incorrect. So in this scenario, maybe you don't notice, or maybe you're like, SpongeBob invades Luxembourg. Nah, hang on. So you need to check it against another authority. So you get this on your laptop, you're like, it's a bit weird. And you get your phone out, you look on that, you're like, all right, well, according to my phone, Biden signed off a tax deal, and you're like, let me check my tablet. All right, okay, so clearly the news is actually the tax deal thing, and there's something wrong with my laptop. I can't trust it. I've got a virus or someone is intercepting my network traffic. I can no longer rely on that system. But maybe you get SpongeBob invades Luxembourg, you get your phone out and it says Mexico just won Eurovision. So you check your iPad and it says NASA's found Brexit opportunities on Mars. And you're like, this is a systemic failure. All of these devices are breaking down, and so you fail over to a completely different system. You go to a store, you buy a newspaper, and you're like, right, give me news that hasn't been filtered through whoever is interfering with my internet. So these are the failure modes that we need to anticipate. Now, the Space Shuttle flew with 5 of these. This is an IBM AP101. It's basically a mainframe in a box. 5 of these on board the Space Shuttle, and the way that they were configured, the way that they were installed was really interesting. 4 of them ran identical copies of the same software. So exactly the same code, same routines, with the same system clock and the same inputs. So all 4 of them are taking telemetry from the same sensors at the same time with the same CPU cycle, and most of the time they agree. The idea is that under normal operation, these will always give you the same output from the same input at the same time. And this means everything is fine. This means everything is working. If one of them suddenly gives you something different, you're like, okay, that is overwhelmingly likely to be a failure of that particular system. Something in that computer has gone wrong. We should stop listening to it. That leaves you with 3. Now, 3 is good enough that you can still get a majority. At this point, you're like, okay, another one's gone wrong. But if you get to here, you don't know which one of these is correct. Now, this is what is known as an abort condition, because the Space Shuttle, they didn't want to lose it in space because the computers couldn't bring it back to Earth. So if you got into this scenario, that was you stop what you're doing and you come home immediately. actually, you had to come home, stop doing what you were doing, and come home immediately if you lost any one computer, because then if you lost another one on the way home, you'd be down to 2, and then you wouldn't know what you were doing if those 2 started disagreeing. So there are safeguards on top of safeguards on top of safeguards. But if these 4 all suddenly started giving contradictory gibberish, at that point, all of the flight telemetry would switch over to the 5th computer, because their analysis, there are a lot of people at NASA working on statistics and probabilities. What is the likelihood that if this thing goes wrong, that thing's also going to go wrong? And this computer was running a completely different set of software written by a different supplier based on the same specification. And their hypothesis was that there might be a bug in System A, running on all those 4. There might be a bug in System B, but there probably wasn't the same bug in the same place in the same code. Neither of these systems was going to be 100% reliable, but if one of them had a problem here, the other one probably didn't have a problem in the same place. So if all 4 of them went haywire, you could fail over to the 5th one, and that was enough to bring the orbiter home. Now, the first couple of shuttle missions, they actually flew with a 6th. They had a spare one on board that wasn't loaded with anything. It was just a, blank computer. The idea being that if they needed to, they could plug this thing in and then go through the procedure to copy all the flight telemetry data across to it. And they flew with this one for about 5 missions. And then Congress and, funding and NASA management were like, it costs a lot of money to send a spare computer into space that we don't use. We could fly cargo with that and, claw back some of the massive amount of money that's being poured into the shuttle program. And so they stopped flying it. Now, as it turns out, the Space Shuttle guidance computer was flawless. It never had a problem. It flew perfectly for the entire lifetime of the Space Transportation System program. But, as I'm sure you're all aware, there were other factors in the shuttle program which had the same kind of attitude to risk. This thing hasn't gone wrong. Maybe we don't need to worry about it anymore, which would go on to have tragic consequences. Now, human beings suck at risk. How many of you are, anyone here afraid of flying? Yeah. Anyone here frightened of taxis? No. Statistically, you are far more likely to get into an accident in a car than you are on an aeroplane. If you spend the same number of hours every year flying as you do driving, the odds are way higher that you'll be in a car accident than that you'll be in a plane accident. But that's not how our brains work, because we ride in cars every day, because cars are safe, right? And, I know people who have been in serious car accidents, and they have a completely different attitude to riding in cabs and, that kind of thing. But, most people, they get on the ground after a flight, and if they're a nervous flyer, they'll be like, I'm down, I survived. And then they'll get a taxi from the airport without even thinking about it. That is the high-risk part of the journey, is the trip to and from the airport, not the bit where you're up in the sky. But we think about planes, and because most of us have never been in a plane crash, our perception of that is based on media, and it's based on stories and Hollywood and television and news headlines. But our perception of riding in cars is we've just spent hundreds of hours riding in cars and nothing really happened. And so we don't really appreciate the amount of risk that's involved. Now, you think about installing a new piece of software, upgrading something, updating something. I've done this dozens of times over the course of my career. And what generally happens is you think, okay, we need to migrate all of our customer data from the old database onto the new CRM platform. And so you'll rehearse it. You'll figure out, okay, what do we need to migrate? When can we do this? What are the dependent systems? What might go wrong? And, you approach this stuff well, and you have the budget and the time to do a good job on it. You will talk to all the people who work on those systems, and you'll be like, can you just keep an eye out for this thing or this thing? Like, these are some things we are worried might not work. And then you roll out the new system, and you keep an eye on it, and probably there's a couple of things go wrong on the first day and the second day, but after a while it kind of settles down. Now, there is a thing called a bathtub curve. It's a graph of failures of a system versus time, and most systems do this. When they are new, they are full of stuff that either just wasn't built right or hasn't kind of been, yet didn't anticipate the load, you didn't anticipate the traffic volume, so you have to jump in and fix a bunch of stuff there. Then everything just kind of rattles along for the lifespan of that system or that product. And then you get to the end of it, and the number of failures starts going up again. And the The reason the failures go up at the end is because when you get to a certain number of failures, you decide that's it. And that is the end of the life of the system. It's now too unreliable. You're not going to use it anymore. But hiding behind the bathtub, these are the early life cycle defects. These are, like I said, the things that, the bugs, the things you didn't get right, the things you missed in your planning and your provisioning. These are the random defects which just kind of rattle along in any system for as long as it's running. And these are the end-of-life defects, which in mechanical systems, this is when parts start to wear out. In software, this is where you can't be bothered to install Windows updates anymore, or, these kinds of things. Because, software doesn't wear out, but you do reach a point where you're like, I can't update this anymore because this thing's incompatible with that thing, and that thing can't be upgraded. So we do still have to anticipate this notion of an engineered lifespan. And really, what these three things mean is it's a new system. Stay alert. Everybody be vigilant. And then you've got the relax. Everything's fine. And then you've got the yeah, bugs, but it doesn't matter. We're getting the new system put in anytime soon. And so people develop a kind of laissez-faire attitude to it. Now, the problem here is that the random defects can often be dismissed as early life cycle defects. You think, okay, the number of bugs for the sort of first iterations of a system, it decreases rapidly, and we naturally think that it's going to tend towards zero. But it doesn't. And so we can get defects in a system that are hiding there, that because they don't blow up early on, we think this is not a problem we need to worry about. The Space Shuttle had protocols for everything. It had the spare computer they carried on board. It had all kinds of mission procedures and parameters and guidelines for how you had to amend or cut short the mission under certain circumstances. But it was also under a huge amount of pressure to keep flying missions. The United States and Congress, they put a huge amount of money and investment into this thing, and they wanted it flying all the time. Every time that they cut short or they delayed a launch, people had to go to meetings and answer questions. And so the pressure was always on, are we being too careful? The protocol says we have to cancel now, but last time we were right on the threshold and we went for it and it was fine. Maybe the protocols are being too stringent. Now, there was a thing called the Space Shuttle Weather Launch Criteria. The shuttle couldn't launch if it was raining. It couldn't launch if the wind was above a certain speed. It couldn't launch if the temperature was above a certain level, but there was no minimum temperature in the launch criteria because it's Florida. Everyone thinks it's warm and sunny. You don't worry about this kind of stuff. Now, in January 1984, they launched the shuttle when it was 13 degrees Celsius outside. It went okay. In January 85, they launched when it was 10 degrees outside. And one of the contractors, a company called Morton Thiokol, they said, we don't think this is a good idea. And NASA said, are you telling us that you are going to accept responsibility for scrubbing the launch? And they went, no, we just think it's not a good idea. And this happened a couple of times, and every time, it went into the record as, Morton Thiokol, who supplied the solid rocket boosters, they have advised that this could be risky, so we flew anyway, and nothing happened. Until 86. Space Shuttle Challenger exploded, 73 seconds after launch. The crew on board were all killed. The temperature that day was 3 degrees Celsius. Now, the investigatory board, they looked into this and they determined that what had caused the explosion was a rubber seal around one of those solid rocket boosters that wasn't resealing properly because it got cold and it got brittle. And the person who actually identified it was this guy. It's Richard Feynman. He's was a Nobel Prize-winning physicist. And they asked him to work on the investigatory board for the Challenger disaster. And then they said, we don't like what you said. We're not going to publish it in the main report. They published it as an appendix. And one of the things that he said in that appendix is the certification criteria used in the flight readiness reviews develops a gradually decreasing strictness. The argument that the same risk was flown before without failure is often accepted as an argument for the safety of accepting it again. Now, imagine you go out in your car one morning and you can't get the seatbelt to lock in properly. And you have to go, you've got to be somewhere. So you drive without a seatbelt. And you're like, all right, well, I did that and I didn't die. And so the next day you do it again, and you book the car into the shop to get it fixed, but it's going to be a couple of weeks. But by the time you take the car in, you've probably been driving around without a seatbelt for 2 weeks, and you're getting used to the idea that it's fine because you've taken the risk and nothing bad has happened, because human beings are terrible at assessing risk. Now, NASA said that the probability of failure of the Space Shuttle program was 1 in 100,000. Feynman said the probability of the Space Shuttle failing was 1 in 100. The shuttle flew 135 missions and lost 2 of them. So he was pretty much bang on the money on his estimate of the reliability of that system. Now, most of us are not working on anything as, historically significant as spaceflight. We probably do have a few enterprise developers in the room, but it's a different kind of enterprise. But we have to anticipate the same kind of, what is the attitude to risk? What is the cost of mitigating that risk? What are the protocols? And are we getting sloppy with ourselves because nothing has gone wrong yet? Now, we live in this glorious age of cloud computing where it is relatively trivial to very quickly provision almost any kind of infrastructure that you need to cope with unprecedented demand. I've been working in IT since the days when you'd look at your business plan for the year and be like, we need to order some servers now so that when they get here in 6 weeks, we have a month to get them set up, put in a rack, switched on, installed, and sitting there doing nothing for hundreds of pounds a month, so that if the business is right about this big spike in July, we're going to have the capacity to deal with it. We had like a 3 to 6 month lead time on that kind of capacity. These days, you can go onto Azure or AWS and go, I need another 100 servers, bang. And it is like, it's like having a company who will deliver a fire extinguisher when you smell smoke. So you don't need to worry about it. You're like, do I smell burning? Yeah, quickly, get me some fire extinguishers. They bring them in, and you just need to make sure that at the point when they arrive, you actually know how to use them. Now, we can build the most wonderfully high availability distributed systems where we can potentially lose an entire continent and the system will just keep on trucking because we've got reverse proxies going into load balancers, going into clustered farms, going to database servers with active replication. The most significant downtime incidents I've ever seen on this kind of infrastructure is because somebody forgot about the single point of failure, which was the limit on the MasterCard on the AWS account that was running it. You got all this lovely stuff. You're like, well, another one of those, and then it's like, you have no money, and we've suspended all your services until you pay the bill. And you're like, we've maxed out. Oops, that may have been a mistake. And at that point, developers are thinking, well, nobody told us we needed a spare MasterCard, because it's not systems thinking. You're thinking that money just comes out of the magical money department, and that's not something that's going to affect your availability, because, hey, we get another server, get another one of these. But to deliver the kind of availability we're talking about, we do need to anticipate failure modes, and we need to understand how our system fits into the bigger system around it, and how that fits into society, and how that fits into the world at large. And these kind of headlines, the headlines about system failures, the thing they all have in common is that people did not anticipate the probability of failure. They thought it was not going to go wrong. In 1995, the UK Post Office Limited installed a new IT system called Horizon. It cost about £1 billion to put this thing together. It was a consultancy installed by Fujitsu who put it together, installed it. Took about 4 years to build. So there you go, nice and agile there. In 1999, they rolled it out into 10 post office branches. They went, yeah, this looks pretty good. They rolled it out across the entire post office network. And shortly after this, it started reporting discrepancies. The Horizon IT system said that money was going missing. The accounts did not add up. Now, I want you to imagine this is you. You have just installed a system, you've done a pilot on 10 offices, it's had 4 years being built by consultants, and then you are going to roll it out across tens of thousands of branches. It's processing a few million transactions per day, and employees are saying, this is wrong. The computer is not adding, it's not giving us the right results. What would you do about it? Because what the post office did about it is they said, we don't care, you are lying, the computer is right, give the money back or you are going to jail. And the employees went, no. And the post office went, yes. Give the money back. If you don't give the money back, we are going to prosecute you for stealing. And they did. And they, 550 branch managers, were prosecuted as criminals because of a computer system that didn't work. Now, they filed a class action lawsuit a couple of years ago that was eventually settled by the Post Office Limited for £58 million. Now, this is Paula Vennells. She's the chief executive of Post Office, or she was. She's also, I think, a Church of England vicar, which tells you everything you need to know. She's basically the person who said, oh, no, it was fine. The employees must have been lying. The message that the board and I were given from the highest levels was that, like any IT system, Horizon was not perfect and had a limited lifespan. It was fundamentally sound. Not perfect, limited lifespan, but you're going to jail anyway. The judge who supervised on the class action lawsuit said, the Post Office's defense amounts in reality to bare assertions and denials that ignore what has actually occurred. It's the 21st century equivalent of maintaining that the earth is flat. Now, this is, for a British High Court judge, this is like seriously passionate, inflamed speech. These people are very, very understated. In 2020, the Criminal Review Commission basically reopened all of these investigations and established that this had been one of the biggest miscarriages of justice in British legal history. Now, this is still going on. There are still investigations and repercussions about this. But what we know is dozens of innocent people had their lives ruined. People cashed in their life savings to pay this back because they didn't want to go to jail. People mortgaged their houses. A couple of people, died of various, illnesses and things while these processes were ongoing. They never got cleared. They were guilty until the day when they were no longer around to fight their corner. And I find that absolutely indefensible. Now, if you've ever worked help desk, or if you've ever worked with human beings and computers at the same time, which, let's face it, we have, you will have had the situation where the computer says one thing and the human being says something else. And you'll have had the thing when you're on help desk and someone phones up and they're like, I had files on my desktop and now they're gone. And you're like, well, you must have deleted them. And the person's like, I didn't delete them. And you're like, I know you deleted them. That's how files on desktops go missing. But you kind of go through the motions. You're like, all right, let me check the backups and I'll call you back. And you don't check the backups. You go and get a cup of coffee and check Reddit and Hacker News. And then you phone them. I'm going, really sorry, I can't find any trace in the backup. Can I come and have a look on your, oh, look, there they are. You've dragged them into the corner. This kind of thing. But if we were talking about tens of thousands of pounds in money, if we're talking about potential criminal charges, I'd check, I'd do the diligence. I think all of you probably would do the same thing. You'd be like, well, maybe the human being is right for once and the computer is wrong for once. And at the very least, we're going to make sure we've investigated all of this before we start giving, handing out criminal prosecutions to people. The consequences of refusing to acknowledge the possibility of failure, they can be tragic, they can be frustrating, they can be trivial. Two-factor authentication is something that is becoming increasingly common. Security has been a big problem for a lot of time. You want to log into your bank account? They're like, we'll send you a text message. I have a friend who lives in London who has no mobile phone reception in her house. For her to log into just about anything important, types it in her laptop, grabs her phone, runs to the end of the street and up a little way so she can kind of hold her phone up like this and hope she gets the code and can then get back to her laptop and type that in. Now, the developers who built that system, they're like, well, it works perfectly. 100% of our text messages were sent. And you're like, but did you think that maybe there's people who don't have reception at the exact place where they are trying to sign into stuff? And they don't, because that's not a software problem. That's a systemic problem. It's a big scale problem. No matter how diligently you plan and anticipate these systems, if all you're looking at is software, real life is going to throw stuff at you that you could not possibly anticipate. This is a recording of the Autopilot system. I'm not sure why we're getting 1 frame per second off the video here. That's interesting. Let me see why that's misbehaving. Yeah. Apparently, the M1 MacBook Pro with the new Apple Silicon will give you 1 frame every 2 seconds. What we have here is a video of a Tesla Autopilot system behind a trailer full of traffic lights. that is getting horribly, horribly confused because it's like, I can see traffic lights, look, there's the traffic lights. And, they never anticipated this. Like, there might be traffic lights in front of the car, which are on their way to somewhere. So we have to, be prepared for these things to crop up. I probably wouldn't have thought of that if I was working on that system, But eventually, someone out there in the real world is going to come back with a scenario, maybe a scenario that they found themselves in that happened to them. And they're going to be like, hey, I was running your Tesla, and there was a truck full of traffic lights in front of me. Sometimes, though, users take the system we built, and they misuse it in the most delightful, ingenious ways, because people are really smart at coming up with ways of using technology that the people who built the technology did not anticipate. A friend of mine used to work for a company who made electron microscopes, really, really kind of high-end, very paranoid about industrial espionage, to the point that even though they had field service engineers all over the world repairing these devices, they had a corporate firewall that didn't let you email attachments. You couldn't send attachments, zip files, XEs, DLLs, couldn't send anything in or out of the building on pain of being fired. You will not violate the corporate policy. You will not send attachments. So you know what they did? Set up a Hotmail box, and everyone had the password. And if you needed something, you'd ring your mate back at head office and go, hey, I need this file. And they would attach it to an email in the drafts folder. And you would sign in and download it, and then you'd delete it. The email never got sent. Nobody broke any rules, but they had a job to do. They had to work around this restriction, which made it difficult. And they're like, well, these are the rules, and this is the problem, and this is the available technology. Let's see if we can figure out a way of making that work. Now, sometimes, you get weird little defects in software which actually turn out to be really significant. Does anyone know what this thing is? This is a Lorenz Attractor. It's a mathematical projection of a chaotic system, but all you need to know about it for this talk is that it's a maths thing that looks pretty and is actually very cool. And it was discovered by this guy. This is Edward Lorenz. And in 1961, he was working on a computer system called the Royal McBee LGP30. Does any of you know a thing called The Story of Mel, a real programmer that kind of floated around the internet for a while? Mel K also programmed one of these things. This was a computer with a 120 kilohertz CPU. It had drum memory. It weighed 360 kilograms. And Lorenz was a meteorologist. He was using this thing to simulate weather. He had built this little weather simulation system, and he would put in a bunch of data for his simulated weather system. He'd set the computer running, and it would print graphs showing temperature or rainfall, some statistic that he was simulating. And one day, he's halfway through running a simulation, something goes wrong, there's a bug in his program, and he thinks, okay, well, that's okay, I can type the data in off the printout, and I can run the simulation again. And what he noticed was the second time he ran the simulation, this happened. It didn't run the same. He's like, this is what's going on. It's the same computer, same program, same inputs, same outputs. And he had a closer look at it, and he realized, after no small amount of head scratching, that the printout was truncated to 3 significant figures, but the computer's memory was accurate to 6 figures. And that that 0.000 something of these numbers was enough to produce a completely different output. And this was the kind of the first moment that he says, by his own admission, he's like, that's the day I realized we'd never be able to forecast the weather. Like, computer weather forecasting was basically doomed, because even this really simplified simulation. But that mistake, that failure in that system actually sowed the seeds for an entirely new branch of science, because chaos theory emerged from that computer bug. And the idea of studying systems which are so dependent on their inputs that if you tweak it by like 1/1000th, you will get radically different output within a very, very short space of time. Now that, I think, is a lovely example of, hey, the computer went wrong, and actually we discovered a whole new branch of science as a result of embracing that failure, Now, weather forecasting, I'm sure you've all done the thing where you lie on your back in a field on a sunny day, and you look at patterns going sort of through the sky, and you recognize them. And we have come up with computer systems that can simulate and mimic the pattern recognition that exists in the human brain. We take a whole stack of labeled photographs, cats and dogs, and we feed them through something called a convolutional neural network. And eventually, we get something out the other end, which is a computer that can tell the difference between, say, I don't know, a dog and a muffin, which doesn't sound difficult. But the beautiful thing about this, this was serious technology. The people who created this are computer vision researchers wanting to be able to do, all sorts of important applications, autonomous vehicles, analysis of crowds, facial recognition for security, airports, these kinds of things. But then a bunch of people were like, this is interesting. You've built a thing that can detect dogs. Now, I turned up yesterday. I quite like dogs. I'm like, we're going to be here for the next couple of days. I wonder if there's any dogs in this building. So I took their dog detector, their neural network, and I ran it across this photograph I took. And it said, we're going to count the number of dogs that are visible in this picture. And what we've determined is there are no dogs here. But that's the point where the users get ingenious. And we're like, no, turn it around. Turn the dog detector into a dog amplifier, run it on this picture, and let's crank up the power. Now, the people who build it are like, you're not supposed to do that. That's not what we created this technology for, but we're like, no, come on. Let's crank up the power. Level 2, level 3, level 4. And I love this kind of serendipity, This is deep dreaming. It's an artistic technique that would never exist if we didn't, one, invent some really, really smart computer systems, and then two, wire them in backwards because we're awkward and we're difficult and we like breaking the rules. And I want to wrap up today by telling you about one of my favorite examples ever of people using technology in a way that they probably weren't supposed to. I grew up in Africa. I was born in Kenya. I spent my childhood in Zimbabwe. When I was a kid, family holidays, you'd get in the back of the car and you'd drive. You'd drive a long, long way, a lot of it on dirt roads without any kind of tarmac. And every once in a while, you'd see in the distance, there'd be like a little red hut or something, and it was always red and white, and it was hand-painted Coca-Cola. And that's where you could stop and get cold drinks and stuff. And within the last kind of 20 years, you could go to places in Africa now that look exactly like that. They are identical, except the little red and white shack in the distance under the tree is still red and white, but it's not Coca-Cola anymore. It's Vodacom. Because cellular networking technology has revolutionized Africa. It's, if any of you saw Richard Campbell yesterday talking about Azure with leapfrog technologies, and Charles Soqualo yesterday was talking about Move Me Back and emerging opportunities in Africa. Africa kind of never got a telephone network because it's a vast continent. You'd need hundreds of thousands of kilometers of cable to get to a village where there are 200 people who have no money. Now, you add into that, there is very little opportunity there for private sector investment, just because you're not going to get that money back. When you factor in, lack of access to resources, corruption is a factor when it comes to government-funded projects, bureaucracy, difficulties in getting things to happen. Africa basically went from having nothing to having cell phones because the bit in the middle was prohibitively expensive, and eventually the technology came in, moving the other way. But something else happened around the same time. This is Nairobi. It's the capital city of Kenya. If you went to Nairobi around the year 2000, just after the whole millennium bug thing kicked off, downtown Nairobi is a modern city. It's got investment banks, five-star hotels, restaurants. There's even a couple of, dot-com internet startups running around there. But you could travel not very far, a couple of hours outside the city, and meet people who had never seen a computer, people who had never made a telephone call, This was the infrastructure challenge. So when they started rolling out cellular network communication technology, it solved the problem of the wiring because you don't need the wires. But what it doesn't solve is the problem of you have a country where nearly 80% of people are what's called unbanked. They don't have bank accounts. So all of the mobile phones that were rolled out in this kind of first launch, they were all pay-as-you-go. And most people didn't have enough money to buy a phone, but there would be someone in your town or your village who did. And so they became almost like a public utility. There would be somebody there who had a phone that you could go and use if you needed to make phone calls. Now, one of the big economic challenges in places like Kenya was there was no way of transferring money. People didn't have bank accounts. So you would, go and get a job in the city, and you'd get paid, and then you'd have money. And you want to send that money home to your family out in the countryside. And you have a couple of choices. One, you can take 4 days off work to make the round trip yourself and give it to them in person. You can't do that every week. And they can't really afford to go without any money for 6 months. Or you put the money in an envelope and you give it to a bus driver who's going in the right direction, and you kind of cross your fingers that 80% of the money will probably make it to the other end within a couple of, this is how it worked. This is the realities of managing that kind of infrastructure. And then somebody worked out that you could take your earnings from your job and you could go into a Safaricom office in downtown Nairobi and you could buy a 250 shilling top-up card, because the top-up card doesn't matter. What matters is the serial number. And then you phone the person in your family's village who has the Nokia, and you're like, I got 250 shillings of top-up for you. And they say, all right, give me the serial number. They top their phone up. So you've just transferred value. Next time your mum goes into the store, shopkeeper's like, hey, I have 200 shillings from your son, and 50 for themselves as, a small handling fee. This was phase one. They had a way, if you had someone on the other end who you kind of trusted, you could transfer airtime by reading out the number. They could top up their phone with that. They would then charge people to come into the shop and make calls. So you had a sort of slightly informal way of transferring money, but then they rolled out the ability to send currency using top-ups. Not to send currency, to send airtime using SMS messages. They built in the facility that if you had a bunch of money on your phone, you could send someone a text message and say, like, here's 100 minutes, or here's 50 shillings worth of airtime credit to friends and family. And people figured out very, very quickly that, okay, one, this is good. You can send money, and then the person on the other end can go in and they can turn it back into cash. They keep the top up, and they give the cash to your family, your mother, whatever. But as people started to trust the system, they're like, well, maybe we don't need to cash out. Maybe we can just send each other airtime. We can send each other minutes as a way of paying for things. And this was the system that kind of got established. People could, someone would start out, they'd earn money, they'd buy a top-up card, they'd put credit on their phone, they'd go to the market, they'd buy a sack of flour, they'd pay with a text message. The person who got the flour would take their kid to the doctor, pay with a text message. And the doctor would need a new tire for the bicycle, they'd go to the bike shop, they'd pay with a text message. The airtime just kept circulating. Now, this is the point where I think a lot of companies would have gone, this isn't working. Like, no one's making phone calls. What was the point in putting in this mobile phone network? All they're doing is texting each other airtime. They're never actually spending it. They're not actually using the credit to make calls. How are we going to make money out of this system? But what Vodafone and Safaricom did is they thought, they're actually onto something here, This is a massive opportunity. And in 2007, I think it was, they launched a system called M-Pesa. For mobile, and Pesa is the Swahili word meaning money. And M-Pesa was a completely bankless, cashless, digital currency system. And M-Pesa is still, trying to shut this down in Kenya right now would be like telling everyone in Europe they're not allowed to use MasterCard anymore. It has become that established. It is the de facto payment solution. Now, this is not phone banking. There is no bank account behind this. Your mobile phone is your digital wallet. And it's not crypto. There is no blockchain or distributed ledger involved. People trust the phone company. That's how this thing works. And the phone, or M-Pesa, the company set up by the phone company, is like, initially this was just, we will let you transfer money backwards and forwards. Then they're like, well, you can have a savings account. We'll pay you interest on this. We will start lending money. We'll do small business startup loans. M-Pesa, it became a route out of poverty for something like 250,000 people. And all of that because the users didn't use it properly. They looked at that piece of tech and they went, oh, they want us to make calls with this? No. I've got a much better idea. And so what I just, that's the sort of thought I want to leave you with, is when you put technology out into the world, anticipate that it is going to go wrong. Don't ever be the person who's like, well, it's not a bug in our software, because maybe your software is a perfect part of a flawed system. Maybe your software doesn't have bugs, but it's doing the wrong thing because you didn't anticipate that you were going to be behind a trailer full of traffic lights going down the freeway. Maybe your email system that you built, it worked perfectly, but the users are getting more value out of it by swapping attachments using the drafts folder. Always be willing to listen to what people are actually doing with your stuff. If they say it doesn't work, listen to them. Maybe there's a problem. Maybe there's an opportunity. Maybe there is something in here that you didn't even think about which could unlock a completely new kind of science or a new kind of commerce or any of these kinds of things. Because no matter how hard we try to ship software which is tested and scalable and has no defects, failure is always an option. Thank you very much. Few minutes for questions, but I'm aware we didn't get a break before this session. So come and find me if you have questions, or go and get coffee. I don't mind. Thank you.